Hello there, and welcome back to the Science Sleepy Minds, that cosy little corner of the universe where we let curiosity and drowsiness hold hands and wander off into the dark together. Tonight, you find yourself standing at the edge of something so incomprehensibly vast that your brain will politely tap out somewhere around the halfway mark, and honestly, that is perfectly fine. You're about to meet the largest star ever discovered in the known universe, a celestial object so absurdly enormous that if you tried to drive around its circumference at highway speed, you would need roughly 900 million years just to complete one lap. You probably would not survive that road trip, but then again, you probably would not survive standing on the surface of this star either. So let us just agree that tonight is about imagination, wonder, and the gentle art of falling asleep to cosmic impossibilities. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're at it, drop a comment telling me where you're listening from tonight and what time it is where you are. I always love picturing this strange global slumber party we have going on, people tucked into beds in Tokyo and Toronto, in São Paulo and Stockholm, all drifting off to the same bizarre astronomical facts. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You begin by shrinking. Not physically, of course, because that would be weird and also probably painful, but mentally. You let your sense of scale dissolve, allow your usual earthbound perspective to melt away like morning frost on a window pane. The room around you fades, the ceiling lifts and keeps lifting, and suddenly you are floating in the velvet blackness between galaxies, a single mote of awareness suspended in an ocean of ancient light. Stars wheel around you in their slow, patient dance, each one a furnace of nuclear fire, each one a story billions of years in the telling. You feel small, wonderfully small, and that smallness is not frightening but liberating. Humans have gazed upward at these distant fires for as long as there have been humans to do the gazing. The ancient Babylonians, those obsessive record keepers of the Mesopotamian plains, catalogued the stars with a precision that still impresses modern astronomers. They carved their observations into clay tablets, tracking the movements of celestial body across the night sky, never quite understanding what those pinpricks of light truly were, but sensing perhaps that they mattered enormously. They developed sophisticated mathematical systems to predict planetary movements, systems accurate enough to forecast eclipses decades in advance. Historians still argue whether the Babylonians genuinely believed stars were divine beings peering down at humanity, or simply useful navigation tools for merchants crossing deserts. But either way, they treated the night sky with a reverence that feels almost quaint in our age of light pollution and smartphone distractions. Here is a quirky little tidbit for you to carry into your dreams. Some ancient cultures believed that stars were holes poked in a great dark blanket draped over the world, allowing the brilliant light of heaven to shine through. The Maori people of New Zealand told stories of the sky being a solid dome with tiny openings. It is a charming image, really. The universe is a kind of cosmic colander, and while we now know that stars are thermonuclear furnaces converting hydrogen into helium at temperatures that would vaporize anything we've ever built, there is something sweetly human about that old blanket theory. We have always wanted the universe to make sense on our terms, to fit into metaphors we can hold in our minds like smooth stones in our palms. But here is the thing about stars that your sleepy brain needs to absorb tonight. They come in sizes. Lots of sizes. Ridiculous sizes. Stars range from tiny red dwarfs barely bigger than Jupiter, simmering along for trillions of years on their meagre fuel supplies, to bloated hypergiants that could swallow entire solar systems without so much as a cosmic burp. The variety is staggering, the range almost offensive to our desire for uniformity and order. And somewhere out there, lurking in the dusty depths of our Milky Way galaxy, sits a star so large that calling it enormous feels like calling the ocean damp. It is technically accurate, but spectacularly insufficient. This star has a name, though calling it a name feels generous. Scientists labelled it Stephenson 2-18, which sounds less like a celestial wonder and more like a particularly uninspired apartment number, or perhaps a tax form nobody wants to fill out. But do not let the bland designation fool you. This star is, as far as we currently know, the largest star ever discovered by human instruments, the absolute champion of celestial enormity. Its radius stretches so far that light itself, travelling at 300,000 kilometers per second, would need over 8 hours just to lap its circumference once. For comparison, light can circle the Earth roughly 7.5 times in a single second. You're beginning to grasp the scale here, or rather, you're beginning to grasp that you cannot actually grasp it, which is honestly the appropriate response. Tonight, you will journey to this impossible star. You will learn how astronomers found it hiding behind curtains of interstellar dust, how they measured it using clever techniques that extract size information from mere pinpricks of light, why they argue about whether it truly deserves the crown or whether some other cosmic giant might claim the throne. You will discover why the biggest stars are not the hottest, a counterintuitive truth that confused astronomers for decades. You will learn why living fast means dying young in the stellar world, why the most massive stars burn through their fuel with reckless abandon and expire in mere millions of years while their smaller cousins persist for billions. And you will understand why the death of a giant like Stephenson 2-18 can seed the birth of worlds like our own, scattering the heavy elements that make up everything from iron cores to human bones across vast stretches of space. But we are getting ahead of ourselves, rushing toward the destination when the journey deserves savouring. Before you can appreciate the extraordinary, you need to understand the ordinary. You need a measuring stick, a baseline, a point of comparison that your pattern-seeking primate brain can actually work with, something familiar to hold against the unfamiliar. And for that, we turn to the most familiar star of all, the one you see every single day without giving it much thought, the one currently fusing 600 million tons of hydrogen into helium every second while you lie here getting drowsy and comfortable. We turn to the sun, that reliable yellow-white presence that has warmed human faces since the first human face existed to be warmed. You drift now toward a question that seems simple, but hides surprising complexity beneath its surface, like a pond that looks shallow from the shore but drops away into unexpected depths the moment you step in. What exactly makes a star large? You might assume the answer is obvious, that big means big, that volume is volume, that you simply measure from one side to the other and call it a day. But astronomy, like most sciences, delights in making simple things complicated, and the concept of stellar size is no exception. Pull up a chair in your mind, get comfortable, and let us untangle this particular knot together. When astronomers talk about the size of a star, they might mean several different things depending on the context, the conversation, and sometimes their mood. They might be discussing radius, which is the distance from the star's core to its outer edge, the most straightforward measurement of physical extent. They might be talking about mass, which is how much stuff the star contains, how many atoms and particles are squeezed together under its gravitational grip, a measurement of substance rather than spread. Or they might be measuring luminosity, the total amount of energy the star pumps out into space every second, a kind of cosmic wattage that tells you how bright the stellar bulb truly burns. Each of these quantities matters, each tells you something important about the star, and each can be used to claim a star is large in some meaningful sense. Here is where things get interesting for your sleepy contemplation. These three measurements do not always line up the way you might expect. The most massive stars are not necessarily the largest in terms of radius. The largest stars are not necessarily the most massive, and the most luminous stars occupy their own complicated category that overlaps with the others in ways that keep doctoral students employed for years at a time, churning out dissertations about stellar classification that approximately 7 people will ever read. The universe does not organise itself for human convenience, much as we might wish otherwise. Consider an analogy that might help clarify this tangle. Imagine you have 2 balloons, both spherical, both the same diameter when measured with a ruler. One balloon is filled with lead pellets, packed tight and heavy, dense as a bad mood on a Monday morning. The other balloon is filled with helium, expanded and airy, light enough to float away if you loosen your grip for even a moment. Both balloons have the same radius, the same volume when you calculate the mathematical space they occupy. But their masses differ dramatically. One would break your toe if you dropped it. The other would drift toward the ceiling and stay there, bobbing gently, judging you for your poor balloon handling skills. Stars work somewhat similarly, though the physics involved are considerably more violent, and the temperatures considerably less compatible with balloon materials. A star's radius depends heavily on its evolutionary stage, on how far along it is in its life cycle, on what kind of nuclear reactions are occurring in its core, and how they balance against the relentless inward pull of gravity. Young main-sequence stars like our Sun maintain a relatively stable balance between the outward pressure of their nuclear fusion and the inward pull of their gravity. They settle into a size that reflects this equilibrium, neither expanding nor contracting significantly over billions of years, just sitting there fusing hydrogen contentedly like cosmic couch potatoes. But stars do not stay young forever. Nothing does, really, which is either depressing or comforting depending on your current mood and perhaps how much sleep you've been getting lately. As stars age, as they begin to exhaust the hydrogen fuel in their cores, strange things start happening. The core contracts while the outer layers expand, sometimes dramatically. A star that spent billions of years as a modest, well-behaved sphere can suddenly balloon outward, puffing up like cosmic bread dough, its radius multiplying by factors of tens or hundreds or even thousands. The transformation can be startling, like watching a sensible accountant suddenly decide to become a professional wrestler. Here is your mainstream historical fact for this stretch of the journey. The Danish astronomer Einar Hertzsprung and the American astronomer Henry Norris Russell independently developed the famous diagram that bears both their names in the early 20th century, between roughly 1905 and 1915. This Hertzsprung-Russell diagram plots stellar luminosity against surface temperature and reveals that stars cluster into distinct groups based on their evolutionary states. Main sequence stars form a diagonal band, red giants occupy an upper right region, white dwarfs huddle in the lower left, and so on. The diagram revolutionized stellar astrophysics by showing that stars follow predictable evolutionary tracks, moving from one region to another as they age and change. Historians still argue whether Hertzsprung or Russell deserves more credit for this foundational tool, but the collaborative nature of scientific discovery tends to blur individual contributions over time, which is either frustrating or beautiful depending on how you feel about the ego-driven nature of academic recognition. And here is your quirky tidbit. The word disaster literally derives from the Latin and Greek words for bad star. Dis means bad or unfavourable, and aster means star. Ancient peoples genuinely believed that certain celestial configurations brought misfortune, that the positions of stars and planets influenced earthly events in direct, causal ways that determined the fates of individuals and empires alike. We now know this is nonsense, of course. that stellar positions have absolutely no bearing on whether you will have a good day or stub your toe or meet a mysterious stranger, but the linguistic legacy remains embedded in our vocabulary. Every time you describe something as a disaster, you're invoking ancient stellar superstition, which is either delightful or mildly embarrassing depending on how you feel about etymology, sneaking astrology into your everyday speech. So when we talk about the largest star ever discovered, we are specifically discussing radius. We are measuring how far the star extends from its centre to its fuzzy, indistinct edge, that outer boundary where stellar atmosphere finally gives way to interstellar space. And we're discovering that some stars extend so far that our usual units of measurement become almost useless. Kilometres feel inadequate, like measuring the ocean in teaspoons. Even astronomical units, those neat little parcels representing the distance from Earth to Sun, start to seem insufficient for the truly massive stars. The largest stars demand their own vocabulary, their own sense of scale, their own category of understanding that stretches the imagination until it creaks. You turn your attention now to something familiar, something you have known your entire life without ever truly knowing it at all. The sun hangs in your mental sky, that brilliant yellow-white disk you were warned never to stare at directly, that celestial presence so constant and reliable that you probably forget it exists most of the time. It rises, it sets, it makes plants grow and skin tan and laundry dry on the line. It has been doing these things since before humans existed, since before the dinosaurs, since before the first fish crawled onto land and wondered what all the fuss was about. But tonight, you are going to give the sun the attention it deserves, because you cannot possibly understand the cosmic giants waiting in the darkness until you first understand this perfectly ordinary star that happens to be yours. The sun is, by stellar standards, remarkably average. It sits comfortably in the middle of the main sequence, that diagonal band on the Hertzsprung-Russell diagram, where most stars spend most of their lives. It is not particularly large, not particularly small, not exceptionally bright or dim, not unusually hot or cool. If stars attended high school, the sun would be that pleasant, unremarkable student who shows up every day, turns in assignments on time, participates adequately in gym class, and graduates without anyone quite remembering their face at the reunion 20 years later. There is no shame in this mediocrity. Most stars are similarly unremarkable, and the universe functions perfectly well with a population dominated by cosmic average performers. But average does not mean unimpressive. The sun's diameter spans approximately 1.4 million kilometers, which means you could line up roughly 109 Earths across its face and still have room to spare at the edges. Its volume could contain about 1.3 million Earths, which sounds like a lot until you realize that some stars could contain millions of suns. But we are getting ahead of ourselves again. Patience is a virtue, especially when contemplating cosmic scale, and the cosmic giants will have their moment soon enough. For now, stay with the sun. Let its familiar warmth anchor you before we venture into colder, stranger territories. The sun's surface temperature hovers around 5,500 degrees Celsius, hot enough to vaporize any known material, hot enough that the very concept of solid matter becomes meaningless at that threshold. Steel melts at roughly 1,500 degrees. Tungsten, the most heat-resistant common metal, gives up at around 3,400 degrees. The sun's surface exceeds these limits comfortably, existing as a roiling plasma of ionized gases rather than anything resembling a solid or liquid surface. And yet, compared to the stars we'll meet later, the sun is positively tepid, a cosmic lukewarm bath rather than a scalding inferno. At its core, where hydrogen atoms slam together and fuse into helium under crushing pressure, temperatures reach approximately 15 million degrees Celsius. This is where the sun's energy originates, in that crushing central furnace where matter converts to energy, according to Einstein's famous equation, where 4 hydrogen nuclei combine to form one helium nucleus and release a tiny burst of energy that, multiplied across countless trillions of reactions per second, powers everything from photosynthesis to sunburns. Roughly 4 million tons of the sun's mass transform into pure radiation every single second. A mass loss that sounds alarming, but represents a negligible fraction of the sun's total bulk, sustainable for billions of years. Here is your mainstream historical fact for this portion of the journey. The ancient Greek philosopher Anaxagoras, working in the 5th century BCE, proposed that the sun was not a deity or a chariot wheel driven across the sky by divine horses, but rather a mass of red-hot metal larger than the Peloponnese Peninsula. This suggestion earned him charges of impiety from the Athenian authorities, and he was eventually exiled from the city for his astronomical heresy, forced to spend his final years in Lampsacus contemplating the ingratitude of democratic governance. The idea that the sun might be a physical object rather than a divine presence genuinely disturbed people, challenged the religious foundations of their society, and threatened the comfortable certainties they had built their worldviews upon. Historians still argue whether Anaxagoras' exile was primarily about his astronomical claims or wrapped up in the broader political tensions of Athenian society, including his association with the controversial statesman Pericles. But either way, the man paid a real price for thinking too carefully about the nature of the sun. Science has always had its martyrs, and here is your quirky tidbit to carry into your dreams. The sun is technically green. No, really, this is not a joke or a trick. If you measured the peak wavelength of light the sun emits, the wavelength at which its blackbody radiation curve reaches maximum intensity, you would find it falls squarely in the green portion of the visible spectrum, around 500 nanometers. We do not perceive the sun as green because it emits a broad spread of wavelengths across the entire visible spectrum, which our eyes and brain blend together into white. Additionally, our atmosphere scatters the blue end of the spectrum more than the red, which makes the sun appear yellow or orange depending on the time of day and the amount of atmosphere the light passes through. But if you were a physics textbook being pedantically accurate, you would have to call our star a green dwarf, which sounds like a small, envious fantasy creature, and probably explains why astronomers quietly ignore this particular classification when talking to the public. The sun has been burning for approximately 4.6 billion years now, and it has roughly another 5 billion years of stable hydrogen fusion ahead of it before things get interesting. Interesting, in this context, means terrifying, at least from the perspective of any Earth-based life that might still be around. When the sun eventually exhausts the hydrogen in its core, it will begin fusing helium instead, and its outer layers will expand dramatically. The sun will become a red giant swelling to perhaps 200 times its current radius, large enough to engulf Mercury entirely, probably Venus as well, and possibly Earth itself depending on orbital evolution effects that remain uncertain. This expansion represents the sun's own modest contribution to the category of stellar bloating we are exploring tonight. Even our average, unassuming star will eventually puff up to impressive dimensions before collapsing into a white dwarf and slowly cooling over trillions of years into a cold, dark cinder. You watch now as a star begins to change, and the transformation you witness contains all the drama of a cosmic metamorphosis, a stellar caterpillar becoming something altogether stranger than any butterfly. This is the process that creates red giants, and understanding it requires you to think about stellar interiors in ways that might feel counterintuitive at first, but will settle into sense as you drift deeper into tonight's lesson. The physics is elegant once you see it clearly, and elegance is restful, so let yourself be carried along by the logic of gravitational collapse and nuclear fire. A star like the Sun spends most of its life in a careful balance, a gravitational standoff between competing forces that neither side can win outright. On one side, you have gravity, that relentless inward pull that wants to crush the star down into the smallest possible space, to squeeze every atom against every other atom until the whole thing collapses into a dense point. Gravity never sleeps, never takes a vacation, never stops pulling. On the other side, you have the outward pressure generated by nuclear fusion, the energy released when hydrogen atoms combine to form helium deep in the stellar core. This energy creates heat. Heat creates pressure, and pressure pushes back against gravity's endless appetite for compression. These two forces push against each other constantly, locked in a standoff, and when they match perfectly, the star maintains a stable size, neither collapsing nor expanding, but hanging in what physicists call hydrostatic equilibrium. This balance can persist for billions of years, which is why stars seem so stable and unchanging from our brief human perspective. The Sun has been roughly the same size for longer than complex life has existed on Earth, longer than fish have swum in oceans, longer than continents have held their current shapes. It will remain roughly the same size for another 5 billion years or so, a constancy that makes it easy to forget that stars are dynamic objects engaged in continuous internal warfare. But nothing lasts forever, not even the patient fusion of hydrogen, and eventually every star runs low on fuel like a car approaching empty on a highway, with no gas stations in sight. When the hydrogen in a star's core begins to run out, the balance tips. Fusion slows because there is less fuel to fuse, outward pressure drops because less energy is being released, and gravity starts winning the ancient tug of war. The core contracts, growing denser and hotter as gravitational energy converts to thermal energy. This contraction might seem like it would make the star smaller overall, and your intuition would be reasonable in expecting this, but stellar physics has a twist waiting for you here. One of those delightful cosmic jokes that keeps astronomers amused and graduate students confused during their preliminary examinations. As the core contracts and heats, a shell of hydrogen surrounding the core, hydrogen that was previously too cool and diffuse to fuse, suddenly finds itself at temperatures high enough to ignite its own fusion reactions. This shell burning, as it is technically called, generates enormous amounts of energy, far more than the core produced during the stable main sequence phase, when everything was proceeding normally. This surplus energy pushes outward on the star's outer layers, inflating them like a balloon attached to an overeager air compressor that someone forgot to turn off. The harder the core contracts, the hotter the shell burns, the more the outer layers expand, in a feedback loop that drives dramatic changes in the star's structure. Here is your mainstream historical fact for this stretch of the journey. The theoretical understanding of stellar evolution, including the red giant phase, was largely developed in the mid-20th century through the pioneering work of astrophysicists like Fred Hoyle, Martin Schwarzschild and others. Hoyle, a British astronomer with a flair for controversy and memorable phrases, made foundational contributions to understanding how stars synthesize heavy elements and how they evolve through different phases. He famously coined the term Big Bang, ironically intending it as a dismissive description of a theory he did not believe in. Schwarzschild, son of the German physicist who solved Einstein's field equations for black holes, developed detailed models of stellar interiors that explained how stars move from main sequence to red giant and beyond. Historians still argue whether the mid-20th century golden age of astrophysics was primarily driven by theoretical insights or by improvements in observational technology. But the synergy between theory and observation during this period fundamentally transformed our understanding of stellar life cycles. And here is your quirky tidbit to lodge in your memory. Some red giants pulsate, expanding and contracting in regular rhythms that can take days, weeks, or even years to complete. These pulsating variables, as astronomers call them, essentially breathe in and out like sleeping giants, their surfaces rising and falling like the chest of some enormous cosmic creature in slumber. The most famous pulsating red giant is probably Mira, a star in the constellation Cetus the Whale, whose brightness varies so dramatically over an 11-month cycle that ancient astronomers sometimes saw it clearly and sometimes could not see it at all, leading them to name it Stellar Mira, the wonderful star or the astonishing star. You are, in a sense, lying here listening to stories about enormous things that breathe, which feels deeply appropriate for a bedtime narrative about cosmic giants and the universe's tendency toward the dramatic. The star expands as all this unfolds, its outer layers cool as they spread across a larger and larger volume, the same amount of energy now radiating from a vastly increased surface area, resulting in lower energy per unit area and therefore lower temperature. This cooling shifts the star's colour from yellow or white toward orange and eventually red, which is why we call these expanded stars red giants. They are giant in radius, having swollen far beyond their main sequence dimensions, and red in hue, their cooler surfaces emitting light shifted toward the lower energy end of the visible spectrum. The name, for once in scientific nomenclature, actually describes the thing it names with reasonable accuracy. The red giant phase represents a significant expansion from main sequence dimensions, but it is still relatively modest compared to what comes next. A star like the Sun, when it becomes a red giant, will expand to perhaps 200 times its current radius. This sounds impressive, and it genuinely is, but stars with greater initial masses can achieve far more dramatic results. You cross now into territory where the ordinary adjectives begin to fail, where words like large and enormous and massive start to feel like understatements of almost insulting proportions. You are entering the realm of the red supergiants, and these stars do not merely differ from their red giant cousins in degree. They differ in kind, occupying a category of stellar extremity that approaches the genuinely absurd, the cosmically ridiculous, the sort of thing that makes you wonder if the universe is showing off for someone's benefit. Perhaps it is showing off for you tonight, as you lie here contemplating impossibilities. Red supergiants form from stars that began their lives with significantly more mass than the Sun, typically at least 8 to 10 solar masses and sometimes considerably more. These massive progenitors burned through their main sequence phases much faster than smaller stars, their greater gravitational pressure forcing fusion to proceed at accelerated rates. The additional mass means additional gravitational squeezing, which means higher core temperatures, which means faster fusion reactions, which means the fuel burns down more quickly despite there being more of it initially. Where the Sun will remain stable for roughly 10 billion years, a star with 20 solar masses might exhaust its core hydrogen in just a few million years, barely a cosmic eye blink, the stellar equivalent of a mayfly's brief summer existence. When these massive stars leave the main sequence, their expansions dwarf anything achievable by Sun-like stars. The core contraction releases enormous gravitational energy, far more than in smaller stars because there is far more mass doing the contracting. The shell burning generates prodigious power, driving the outer layers outward with tremendous force, and those outer layers inflate to radii measured in hundreds of millions of kilometers, dimensions that start to approach the scale of planetary orbits. A typical red supergiant might achieve a radius between 500 and 1,000 times that of the Sun, volumes so vast that if you placed one where the Sun currently sits, its surface would extend well past the orbit of Mars and possibly reach toward Jupiter, swallowing everything in between without apparent effort. The most famous red supergiant is almost certainly Betelgeuse, that reddish star marking the shoulder of Orion the Hunter in the winter sky. You've probably seen it without knowing what you were looking at. A reddish-orange beacon distinguishing itself from the blue-white stars that dominate Orion's other corners. Look up on a clear winter night, find the distinctive three-star belt of Orion, and then look to the upper left corner of the constellation. That rust-coloured point of light is Betelgeuse, one of the largest stars visible to the naked eye, roughly 700 light-years from Earth, and yet bright enough to catch your attention across that immense gulf. Betelgeuse has a radius approximately 700 to 1,000 times that of the Sun, depending on how you measure its fuzzy, indistinct outer boundary, and it pulses irregularly, its brightness fluctuating in ways that keep astronomers perpetually uncertain about what exactly is happening in its turbulent interior. Here is your mainstream historical fact for this stretch of the narrative. The name Betelgeuse derives from Arabic astronomical terminology, specifically from a phrase that medieval translators rendered into Latin and then into various European languages over the centuries. The original Arabic likely meant something like the hand of Orion, or possibly the armpit of the central one, referring to Orion's anatomy as imagined by Arabic stargazers. Arabic astronomers preserved and expanded upon Greek astronomical knowledge during the medieval period, maintaining the flame of systematic observation, while much of Europe languished in relative intellectual dormancy. Many star names in use today reflect this Arabic heritage, including Aldebaran, the follower, Altair, the flying one, and Rigel, the foot. Historians still argue whether the transmission of astronomical knowledge from Greek to Arabic to Latin sources involved significant original contributions by Arabic scholars or primarily faithful preservation of earlier work, but the star names themselves testify to a genuinely multicultural scientific heritage that spans millennia and civilizations, and reminds us that knowledge has always been a collaborative human project. And here is your quirky tidbit to carry into your dreams. Betelgeuse dimmed dramatically in late 2019 and early 2020, losing roughly 2/3 of its normal brightness over the course of a few months, a change visible even to casual observers who knew where to look. Astronomers and amateur skywatchers alike speculated that the star might be about to explode as a supernova, which would have been the astronomical event of several lifetimes, visible in broad daylight and potentially brighter than the full moon for weeks. The dimming turned out to result from a combination of cooling in the star's photosphere and a cloud of dust expelled by the star itself, blocking some of its light from reaching Earth. Betelgeuse was essentially having a cosmic sneeze, expelling material and temporarily obscuring itself, not experiencing a death rattle, though the supernova will eventually come, possibly within the next 100,000 years, which counts as imminent in stellar terms, though not exactly urgent on human timescales. Red supergiants like Betelgeuse inhabit the upper right corner of the Hertzsprung-Russell diagram, the region reserved for stars that are simultaneously very luminous and relatively cool. This combination sounds paradoxical until you remember that luminosity depends on both temperature and surface area. A cooler star can outshine a hotter one simply by having vastly more surface area from which to radiate energy, and red supergiants have surface areas that boggle the imagination, that break the mental calculator, that leave you blinking and confused. The surfaces of these stars are not solid, of course. Nothing about a star is solid in any meaningful sense. The very concept of solid matter requires temperatures low enough for electrons to settle into stable orbits around nuclei, conditions incompatible with stellar existence. The photosphere, that visible outer layer from which light escapes into space, represents merely the depth at which the stellar material becomes transparent enough to let photons through. In red supergiants, this photosphere is remarkably thin relative to the star's overall size, a wispy boundary between the opaque interior and the transparent exterior, constantly churning with convection currents that dwarf entire planets. If you could somehow stand on the surface of a red supergiant, which you absolutely could not because you would be instantly vaporized, and also there is no surface to stand on, you would witness a landscape of unimaginable turbulence. Convection cells the size of Earth's orbit would rise and fall, carrying superheated plasma from the interior in slow-motion eruptions. You arrive now at the destination you've been travelling towards since this journey began, the star that currently holds the record for the largest known stellar object in the observable universe. Its name is Stephenson 218, and its dimensions are so extreme that your brain will likely refuse to fully process them, which is a reasonable form of self-protection given the circumstances. Some things are not meant to be comprehended completely, only approached with humility and wonder, and this star definitely qualifies. So take a breath, settle deeper into your pillow, and let the numbers wash over you like warm water, cleansing you of any lingering attachment to human-scale thinking. Stephenson 218 sits approximately 20,000 light-years from Earth, lurking in a heavily obscured region of the Milky Way near the constellation Scutum. To put that distance in perspective, light leaving this star right now will not reach Earth until the year 22,000 or so, by which time human civilization will have either spread across the galaxy, destroyed itself, or evolved into something unrecognizable, depending on which science fiction scenario you find most plausible. The star hides behind vast clouds of interstellar dust, cosmic curtains that absorb and scatter visible light, which is why you cannot see it with the naked eye despite its tremendous intrinsic brightness. It reveals itself primarily in infrared wavelengths, that portion of the electromagnetic spectrum that passes more easily through dust, and it was in infrared surveys that astronomers first recognized just how extraordinary this object truly is. The star takes its name from Charles Bruce Stephenson, an American astronomer who catalogued a cluster of massive stars in this region back in 1990. Stephenson spent his career at Case Western Reserve University in Ohio, patiently surveying the sky with photographic plates and cataloguing what he found. The kind of unglamorous systematic work that forms the foundation upon which dramatic discoveries are built. The cluster he identified, designated Stephenson 2, contains numerous enormous stars clustered together in the same region of space, siblings born from the same massive molecular cloud. But one member of this stellar family stands out even among this extraordinary company, distinguished by its sheer incomprehensible size. The radius of Stephenson 218, according to current estimates, stretches to approximately 2,150 times the radius of the Sun. Stop for a moment and let that number settle into your increasingly drowsy consciousness. 2,150 solar radii. The Sun is already impressive, already a sphere that could contain over 1 million Earths, and this star exceeds the Sun's radius by a factor exceeding 2,000. If you place Stephenson 218 at the centre of our solar system, its surface would extend well past the orbit of Saturn, possibly reaching toward Uranus depending on which measurement uncertainties you prefer and how you define the fuzzy boundary of such a tenuous object. Mercury, Venus, Earth, Mars, Jupiter and Saturn would all be engulfed, simply absorbed into the star's vast outer atmosphere, vaporized and incorporated into the stellar plasma without so much as a ripple. Here is your mainstream historical fact for this portion of the journey. Charles Bruce Stephenson himself passed away in 2001, just a few years before the full extremity of his namesake star became apparent through improved measurements and analysis. He spent his career doing the patient cataloguing work that makes discoveries possible, never quite knowing that one of his catalogued objects would turn out to be the largest known star in the entire observable universe. There is something poignant about this, the discoverer departing before understanding the full significance of what he found, like a gardener planting seeds for trees whose shade they will never enjoy. Historians still argue whether astronomical discovery should credit the person who first observes an object or the person who first understands its significance. But in this case, both Stephenson and the later researchers who analysed his catalogued cluster deserve recognition. And here is your quirky tidbit to carry into your dreams. The constellation Scutum, where Stephenson 2-18 resides, is one of the smallest and least prominent constellations in the entire sky, covering only about 109 square degrees compared to the 1,303 square degrees covered by Hydra, the largest constellation. Scutum's name means shield in Latin, and it commemorates the victory of King John III Sobieski of Poland at the Battle of Vienna in 1683, when Christian forces turned back the Ottoman siege of the Austrian capital. The astronomer Johannes Hevelius created the constellation specifically to honour this military achievement, making it one of the few constellations with a documented political origin and a specific historical event behind its naming. The irony that the largest known star hides in one of the smallest, most obscure constellations feels almost deliberately poetic, as though the universe enjoys a quiet joke at the expense of human pattern seeking and our tendency to assume that important things should be prominently displayed. Stephenson 2-18 belongs to a category of stars sometimes called red hypergiants, objects that exceed even the impressive dimensions of ordinary red supergiants. The distinction between supergiant and hypergiant remains somewhat fuzzy in astronomical terminology, with different sources using different criteria, but the basic idea involves stars that push toward the theoretical upper limits of how large any stellar object can grow. These limits exist because at some point a star becomes so large and tenuous that its outer layers can no longer maintain gravitational cohesion. The star begins to lose mass through powerful stellar winds, material streaming away into space faster than the star can expand further, setting a practical ceiling on stellar dimensions. The surface temperature of Stephenson 2-18 hovers around 3,200 Kelvin, which makes it cooler than a typical household candle flame and roughly half the temperature of the Sun's surface. This coolness might seem surprising for something we call a star, but it reflects the fundamental physics we discussed earlier. As a star's surface area increases, it can radiate the same total energy at lower temperatures, spread the same amount of heat across a much larger surface, and each portion of that surface can be cooler while still radiating the same total power. Stephenson 2-18 radiates with a luminosity approximately 440,000 times that of the Sun, tremendous power that spreads across a surface area millions of times greater than solar, resulting in that relatively modest surface temperature and the deep red colour characteristic of cool stellar objects. You have met the current champion, the reigning monarch of stellar enormity. But every monarch has rivals, and every record has challengers. You wonder now how anyone could possibly measure something so distant and so vast, how astronomers sitting on this small planet could determine the radius of a star 20,000 light-years away, hidden behind curtains of interstellar dust, its light travelling for millennia before reaching the instruments that analyse it. The question deserves a thoughtful answer, because the methods involved represent some of humanity's cleverest scientific achievements, the application of physics and mathematics to extract information from pinpricks of light that seems almost magical until you understand the principles behind it. So let yourself drift into the realm of measurement and methodology, where precision emerges from patience and careful reasoning. Most stars, even through the most powerful telescopes humans have ever built, appear as mere points of light. Their distances are so immense that their actual physical dimensions cannot be directly observed, The light arrives as a pinprick regardless of the star's true size, offering no obvious visual indication of whether you're looking at something the size of the Sun or something 2,000 times larger. This fundamental limitation might seem to make stellar measurement impossible, and indeed for centuries astronomers had no reliable way to determine stellar sizes, leaving them to speculate and argue without definitive resolution. But modern astronomy has developed several indirect methods that extract size information from starlight without ever actually seeing the stellar surface as a resolved disk. The most straightforward approach involves a combination of luminosity and temperature, two quantities that can be measured independently and then combined through known physical relationships to yield a radius estimate. If you can determine how much total energy a star radiates per second, which is its luminosity, and you can determine the temperature of its surface, which affects how much energy it radiates per unit of surface area according to well-established physics, then you can calculate how much surface area the star must have to produce that observed luminosity at that observed temperature. The calculation follows directly from the Stefan-Boltzmann law, that fundamental equation linking temperature, surface area, and radiated power, written down in the 19th century and verified countless times since. More surface area means a larger star, and the relationship is precise enough to yield reasonably reliable estimates even for objects impossibly far away. Here is your mainstream historical fact for this portion of the journey. The first reliable stellar distance measurement was accomplished by the German astronomer Friedrich Bessel in 1838, when he detected the parallax shift of the star 61 Cygni. Parallax involves measuring how a star appears to shift position against more distant background stars as Earth orbits the Sun, essentially using Earth's orbit as a baseline for triangulation. Bessel measured the tiny angular shift of 61 Cygni over the course of a year, and from that shift, barely a fraction of an arc-second, he calculated a distance of about 10.3 light-years, remarkably close to the modern accepted value of 11.4 light-years. This achievement represented the first time humans had genuinely measured the distance to another star using geometric methods, confirming that the cosmos extended vastly farther than our solar system and opening the door to understanding stellar properties. Historians still argue whether Bessel's measurement or the near-simultaneous measurements by Thomas Henderson of Alpha Centauri and Friedrich Georg Wilhelm Struve of Vega deserve priority, but all three astronomers contributed to the fundamental understanding that stars occupy a three-dimensional space of genuinely cosmic dimensions. And here is your quirky tidbit to lodge in your memory. The unit of distance called a parsec, commonly used in professional astronomy, derives directly from parallax measurements. 1 parsec is defined as the distance at which a star would show a parallax angle of exactly 1 arc-second, and it works out to approximately 3.26 light-years. The name cleverly combines parallax and arc-second into a portmanteau that sounds vaguely scientific fictional, which may explain why the Star Wars franchise incorrectly used it as a unit of time rather than distance when Han Solo bragged about completing the Kessel Run in less than 12 parsecs. This error has irritated astronomers for decades while spawning elaborate fan theories about what Solo might have actually meant, none of which are as satisfying as simply accepting that screenwriters sometimes get technical details wrong. For extremely distant stars like Stephenson 2-18, direct parallax measurements become impractical. The parallax shifts are simply too tiny to detect reliably at distances of thousands of light-years, fractions of milliseconds that push against the limits of even space-based measurement platforms. Instead, astronomers rely on indirect distance indicators, methods that use known relationships between stellar properties to estimate how far away an object must be. One powerful technique involves stellar clusters. If Stephenson 2-18 belongs to the Stephenson 2 cluster, and if that cluster's distance can be estimated through other means, then the star's distance follows by association. Cluster distances can be determined through main sequence fitting, where astronomers compare the brightness of cluster members to theoretical models of stellar evolution, identifying the distance that makes the observations consistent with the models. Another approach uses the interstellar medium itself as a distance indicator. As starlight travels through space, it passes through clouds of gas and dust that absorb and redden the light in predictable ways, the blue wavelengths scattered more than the red, leaving a characteristic signature that can be measured. By analysing this interstellar extinction, astronomers can estimate how much material lies between Earth and the star, which provides a rough sense of distance along the line of sight. The more extinction, the more intervening material, and generally the greater the distance, though this relationship depends on the distribution of dust along different sight lines through the galaxy. For surface temperature, astronomers rely on spectroscopy, analysing the specific wavelengths of light the star emits and absorbs. Different temperatures produce different spectral signatures, characteristic patterns of bright and dark lines that act like cosmic fingerprints, revealing the physical conditions in the stellar atmosphere. Hot stars show different spectral features than cool stars, and the relationship is well enough understood that temperature can be determined within a few hundred degrees, even for objects impossibly far away. All these methods carry uncertainties that compound when calculating stellar radii. The estimated radius of Stephenson 2-18 might be off by significant margins, which is why astronomers speak carefully about the largest known star rather than claiming absolute definitive records. You attempt now to visualize what these measurements actually mean, to translate the abstract numbers into something your imagination can grasp, as you lie there growing drowsier by the minute. The radius of Stephenson 218 stretches approximately 2,150 times farther than the Sun's radius, and while that number has meaning on paper, your pattern-seeking brain craves something more tangible, something it can wrap itself around and carry into dreams. Numbers alone rarely satisfy the human desire for understanding. We need images, comparisons, stories that make the vast feel graspable, even when true comprehension remains forever out of reach. Begin with the Sun itself, that familiar yellow-white disk roughly 1.4 million kilometers in diameter, a sphere you could circumnavigate about 109 times at Earth's width. Now imagine inflating it, watching it swell like a balloon on a cosmic scale, its surface pushing outward while its colour shifts from yellow-white toward orange, then deeper toward red as the surface cools with expansion. At 10 solar radii, the inflated Sun would engulf Mercury's orbit, that innermost planet vanishing into stellar material without a trace. At 50 solar radii, Venus would follow, consumed by the expanding photosphere. At 100 solar radii, Earth's orbit would be reached, our planet's position now deep within the stellar atmosphere rather than safely outside it. At 200 solar radii, roughly the size the Sun itself will achieve during its red giant phase, Mars would be approached or swallowed. Keep inflating. At 500 solar radii, the star extends beyond the main asteroid belt, reaching toward Jupiter's orbital distance. At 1,000 solar radii, Jupiter itself would be engulfed, that mighty gas giant reduced to a brief disturbance in the stellar plasma before being incorporated into the star's bulk. At 1,500 solar radii, Saturn's orbit falls within the stellar boundary. And at 2,150 solar radii, at the estimated size of Stephenson 218, the star's surface lies somewhere between the orbits of Saturn and Uranus, depending on which measurements you prefer and how you define the fuzzy edge of such a tenuous object. Everything from the innermost rocky worlds to the gas giants, everything we typically think of when we picture our solar system, would exist inside this single star. Here is your mainstream historical fact for this portion of the journey. The concept of light having a finite speed, rather than travelling instantaneously across any distance, was first demonstrated experimentally by the Danish astronomer Ole Rømer in 1676 using observations of Jupiter's moon Io. Rømer noticed that the timing of Io's eclipses behind Jupiter, events that should occur at regular predictable intervals, actually varied depending on whether Earth was moving toward or away from Jupiter in its orbit. When Earth was approaching Jupiter, the eclipses seemed to come slightly early. When Earth was receding, they seemed slightly late. Rømer correctly interpreted this variation as resulting from the time light took to cross the changing distance between Earth and Jupiter, and his estimate of light's speed, while not perfectly accurate by modern standards, established the fundamental principle that light travels at finite velocity. This insight, that light requires time to cross distances, transformed astronomy and eventually physics, laying groundwork for everything from stellar parallax measurements to Einstein's relativity. Historians still argue whether Rømer fully understood the implications of his discovery or viewed it primarily as a correction factor for astronomical timing, but the measurement opened doors that would not be fully explored for centuries. And here is your quirky tidbit to carry into your dreams. If you tried to fly around the circumference of Stephenson 218, in a commercial airplane travelling at typical cruising speed, roughly 900 kilometers per hour, the journey would take approximately 1 billion years. 1 billion years of continuous flight, no stops for fuel or food or bathroom breaks, just endless motion around the perimeter of a single star. The airline miles would accumulate impressively, but you would not live to use them, and the in-flight movie selection would become repetitive long before you completed even a tiny fraction of the journey. You might manage to watch every film ever made several million times over, which sounds less like travel and more like a very specific circle of hell. Light fares better, but still requires impressive patience. Light, travelling at approximately 300,000 kilometers per second, fast enough to circle Earth 7.5 times in a single heartbeat, would require over 8 hours to travel from one side of Stephenson 218 to the other if it traced a path straight through the star's centre. 8 hours of travel at the fastest speed the universe permits, covering a distance roughly equivalent to the space between the Sun and Pluto and back again, and you would only just have crossed a single star. The scale mocks our intuitions, exceeds our experiential vocabulary, demands new mental categories that we must construct from scratch. The volume comparisons become even more staggering when you calculate them, though at a certain point the numbers lose all intuitive meaning and become merely symbols on a page, impressive sounding but emotionally empty. Because volume scales with the cube of radius, Stephenson 218's volume exceeds the Sun's by a factor of roughly 10 billion. 10 billion suns could fit inside this single star, packed like cosmic marbles into a fishbowl the size of the outer solar system. And since the Sun itself could contain about 1.3 million Earths, Stephenson 218 could theoretically contain approximately 10 quadrillion Earths, a number so large it becomes almost meaningless, a string of digits signifying nothing your experience can anchor. The mass of Stephenson 218, interestingly, does not scale with its volume. This star, despite its enormous size, contains only perhaps 12 to 16 times the mass of the Sun. The vast majority of its volume consists of extremely tenuous gas, plasma so thin it would qualify as a decent laboratory vacuum by terrestrial standards. The star is, in essence, a cosmic soap bubble, beautiful and vast and surprisingly empty, its immense size reflecting the extreme expansion of a relatively modest amount of matter across an impossibly large space. Enormous in extent, modest in substance, proof that size and mass are very different things. You zoom out now from the star itself to consider the neighbourhood it inhabits, because Stephenson 218 does not drift alone through the galactic void like a solitary wanderer. It sits embedded within a cluster of similarly enormous stars, a cosmic nursery where giants grow together like redwoods in a primordial forest, their roots tangled in shared gravitational wells, their crowns reaching toward the same dark sky. This cluster, designated Stephenson 2, represents one of the most massive stellar assemblages in the entire Milky Way, a concentration of stellar enormity that helps explain how stars like Stephenson 218 come to exist at all. The context matters because stars are social creatures, born in groups, living in communities, and the environment of their birth shapes everything about their subsequent existence. Stellar clusters form when giant molecular clouds collapse under their own gravity, fragmenting into multiple dense cores that each become individual stars. Picture a vast cloud of hydrogen and helium, hundreds of light years across, cold and dark and patient, drifting through the galaxy for millions of years. Then something disturbs the cloud, perhaps a shock wave from a nearby supernova, perhaps gravitational perturbations from passing through a spiral arm, perhaps just random turbulence exceeding some critical threshold. Parts of the cloud begin to fall inward, pulled toward their own centres by gravitational attraction, and as they fall they fragment further, breaking into smaller and smaller pieces until each piece achieves sufficient density to begin collapsing independently. The resulting cluster contains stars that share approximately the same age and chemical composition, born from the same reservoir of interstellar material within a cosmically brief period, siblings with shared parentage if not identical genetics. Some clusters remain loosely associated for billions of years, their member stars drifting gradually apart under the influence of galactic tides and random gravitational encounters, eventually dispersing into the general stellar population. Others, like Stephenson 2, stay more tightly bound, their collective gravity holding the stellar family together against dispersing influences, maintaining their identity as a distinct grouping across astronomical timescales. The Stephenson 2 cluster has remained coherent long enough for its massive stars to evolve into red supergiants, which tells us something about both its age and its gravitational binding. Here is your mainstream historical fact for this portion of the journey. The existence of stellar clusters has been recognised since ancient times, with the Pleiades star cluster mentioned in texts ranging from Homer's Iliad to the Bible's Book of Job to the poems of the Chinese poet Du Fu. These naked-eye visible clusters, tight groupings of stars distinguishable from the scattered background, were interpreted variously as divine signs, seasonal markers, agricultural timers, and navigation aids across dozens of cultures spanning thousands of years. The scientific understanding that these groupings represent physically associated stellar families, rather than merely chance alignments along the line of sight, developed gradually through the 17th, 18th and 19th centuries as telescopes revealed their true nature. William Herschel, the great German-British astronomer who discovered Uranus, conducted extensive surveys of clusters and nebulae, laying groundwork for understanding their physical reality. Historians still argue whether certain ancient references to stellar clusters reflect genuine astronomical knowledge or merely poetic license, but the cultural importance of these celestial groupings across diverse civilizations seems beyond reasonable dispute. And here is your quirky tidbit to carry into your dreams. The total mass of the entire Stephenson 2 cluster has been estimated at roughly 40,000 solar masses, making it one of the most massive stellar clusters in the galaxy, and qualifying it as what astronomers call a red supergiant cluster, a rare type of cluster characterized by containing numerous red supergiants simultaneously. If all that mass was somehow compressed into a single object, which is not how physics works but makes for an interesting thought experiment. It would have enough gravitational pull to significantly perturb the orbits of nearby stars, becoming a notable gravitational player in its galactic neighbourhood. Of course, the mass remains distributed across thousands of individual stars, each following its own orbit within the cluster's collective gravitational well, dancing together in a complex choreography that will continue for millions of years until the cluster eventually disperses or its most massive members explode. The Stephenson 2 cluster lies in the direction of the constellation Scutum, roughly 20,000 light-years from Earth, in a region heavily obscured by interstellar dust. This obscuration explains why the cluster remained largely unknown until infrared surveys pierced the dusty veil in the late 20th century, revealing the brilliant giants hidden behind curtains of absorbing material. The cluster contains at least 26 red supergiant stars, an extraordinary concentration of stellar enormity that makes it one of the most remarkable stellar assemblages known to astronomy. Finding this many red supergiants in one place is like finding an entire football team of professional athletes in a small town. It suggests special circumstances, unusual conditions that favour the production of exceptional individuals. The presence of so many red supergiants in a single cluster tells astronomers something important about the cluster's age. Massive stars evolve faster than less massive ones, reaching the red supergiant phase more quickly and dying sooner. A cluster rich in red supergiants must be young enough that these short-lived giants have not yet exploded as supernovae, but old enough that they have had time to evolve off the main sequence and expand into their current bloated states. This places Stephenson 2's age at roughly 14 to 20 million years, ancient by human standards but cosmically adolescent, barely a flicker in the galaxy's multi-billion-year history. The environment within such a cluster differs significantly from the relatively empty space around isolated stars like the Sun. Stars crowd closer together, their gravitational influences overlapping, their stellar winds interacting and sometimes colliding in shock waves that heat the interstellar medium between them. The space between cluster members contains enriched material, heavy elements forged in previous generations of stars and scattered by their deaths, ready to be incorporated into the next generation of stellar systems. This enrichment matters profoundly for the future, for planet formation, for the eventual emergence of complexity, and perhaps life itself. The atoms in your body were forged in stars, and many of those stars likely lived and died in clusters not unlike Stephenson 2, their death seeding the cosmos with the raw materials for everything that came after. You rewind now through cosmic time, travelling backward to witness the birth of a giant, the violent and beautiful process that brings stars like Stephenson 218 into existence from nearly nothing at all. This is not a gentle nativity, not a peaceful emergence into being, but rather a catastrophic collapse, a gravitational avalanche that transforms diffuse gas into concentrated nuclear fire across timescales that would seem instantaneous to a star but agonizingly slow to any human observer. The story of stellar birth is a story of gravity winning, of matter surrendering to its own weight, of chaos organizing itself into something luminous and powerful. Let yourself drift into this primordial drama, this cosmic creation story written in the language of physics rather than mythology. The story begins with a giant molecular cloud, one of those vast reservoirs of gas and dust that drift through galaxies like cosmic fog banks, obscuring the stars behind them and nurturing the stars within them. These clouds are enormous beyond easy comprehension, extending across hundreds of light years, containing enough material to form millions of stars if all of it were to collapse and fragment appropriately. They consist primarily of hydrogen and helium, the primordial elements left over from the Big Bang, along with traces of heavier elements contributed by previous stellar generations that lived and died and scattered their enriched ashes across space. The clouds remain remarkably cold by cosmic standards, often just 10 or 20 degrees above absolute zero, cold enough that the molecules within them move sluggishly, cold enough that thermal pressure provides minimal resistance to gravitational collapse. Something disturbs the cloud. Perhaps a nearby supernova sends a shockwave rippling through the material, compressing regions that were previously stable into configurations that exceed the critical threshold for collapse. Perhaps the cloud passes through a spiral arm of the galaxy, where tidal forces squeeze and stretch the gas like cosmic taffy. Perhaps some internal turbulence creates a random overdensity that happens to exceed what physicists call the Jeans mass, the minimum amount of material needed for gravitational attraction to overcome thermal pressure. The trigger varies from cloud to cloud, from star to star, but the result is consistent. Parts of the cloud begin to fall inward, pulled toward their own centers of mass by gravitational attraction, and the collapse has begun. Here is your mainstream historical fact for this portion of the journey. The theoretical framework for understanding stellar birth was largely developed by the British physicist James Jeans in the early 20th century, building on thermodynamic principles established in the 19th century. Jeans derived the critical mass required for a gas cloud to collapse under its own gravity, a threshold now called the Jeans mass in his honour, and he showed how this threshold depends on the temperature, density and composition of the cloud. His equations explained why only certain regions of interstellar space form stars, while other regions remain stable clouds indefinitely, dispersing rather than condensing. The mathematics are elegant, relating fundamental physical quantities through derivations that any physics graduate student can follow, and yet they describe processes of almost unimaginable violence and scale. Historians still argue whether Jeans fully appreciated the implications of his stability criterion for understanding the universe's stellar population, or viewed it primarily as an interesting mathematical exercise with limited practical application. But his work laid the foundation for modern theories of star formation that continue to be refined and tested today. And here is your quirky tidbit to carry into your dreams. The very first stars in the universe, those that formed from pristine hydrogen and helium without any trace of heavier elements, may have been even larger than Stephenson 2-18, perhaps dramatically so. These hypothetical primordial giants, sometimes called population 3 stars by astronomers who enjoy confusing naming conventions, have never been directly observed despite extensive searches. Theoretical models suggest they could have reached masses of several hundred solar masses and radii that might have exceeded anything we see in the modern universe. They burn through their fuel almost instantly by cosmic standards, perhaps living only a few million years before exploding as supernovae and seeding the universe with the first heavy elements, making possible everything that came after, including the carbon in your cells and the iron in your blood. Every atom in your body heavier than hydrogen and helium was forged inside a star and scattered by stellar death, which makes you quite literally star stuff contemplating stars. As the collapsing region of a molecular cloud condenses, it fragments into smaller cores, each destined to become a separate star. The fragments compete for material from their surroundings, with the largest and densest accumulating the most gas and growing fastest. A feedback process develops where the more massive a core becomes, the stronger its gravitational pull, and the faster it accretes additional material from the common reservoir. This competitive accretion produces a range of stellar masses within a single cluster, from modest sun-like stars that will live for billions of years to massive giants that will burn through their fuel in mere millions. The cores destined to become the most massive stars collapse fastest, their greater gravity accelerating the inflow of material. creating dense concentrations of matter surrounded by spinning disks of debris that may eventually form planetary systems. Within perhaps 100,000 years, a timescale that sounds long but represents a cosmic eye blink compared to stellar lifetimes, the core temperature rises high enough to initiate nuclear fusion. Hydrogen atoms, stripped of their electrons by the intense heat and pressure, begin slamming together and combining to form helium, releasing energy in the process. Nuclear fire ignites in the center of the collapsing mass, and a star is born. The outward pressure of this fusion finally halts the gravitational collapse, establishing the hydrostatic equilibrium that will persist through the star's main sequence life, the balance between gravity pulling inward and fusion pushing outward that defines stellar existence. For a massive progenitor star like the one that would eventually become Stephenson 218, the main sequence phase burns hot and brief. The star fuses hydrogen at a furious rate, its high-mass core driving reactions far faster than lower-mass stars can achieve, shining with tremendous luminosity visible across enormous distances. But this brilliance comes at a cost measured in time. You encounter now the uncomfortable reality that measurements at cosmic distances involve significant uncertainty, that the confident-seeming numbers astronomers report in scientific papers and popular articles conceal margins of error large enough to swallow entire planets. The size of Stephenson 218 is not known with the precision you might expect from modern science, but rather estimated within ranges that leave room for scholarly debate, disagreement, and occasionally heated arguments at astronomy conferences. This uncertainty is not a failure of scientific methodology or a limitation waiting to be overcome, but rather an honest acknowledgement of how genuinely difficult these measurements truly are when your subject sits 20,000 light-years away and hides behind curtains of interstellar dust. The primary sources of uncertainty in stellar radius, estimates, involve distance and temperature, the two fundamental quantities that feed into the calculation. To determine a star's radius, astronomers typically measure its apparent brightness as seen from Earth, estimate its distance to convert apparent brightness into true luminosity, measure its surface temperature through spectroscopic analysis, and then use the Stefan-Boltzmann law to calculate how much surface area is needed to radiate that luminosity at that temperature. Each step in this chain introduces its own uncertainties, and those uncertainties propagate through the calculation, compounding in ways that can produce significant ranges in the final result. If the distance to Stephenson 2-18 is overestimated by 20%, the calculated luminosity drops by roughly 40%, because luminosity scales with the square of distance and the derived radius decreases correspondingly. If the surface temperature is underestimated by a few hundred degrees, the star appears to need more surface area to produce its observed luminosity, since cooler surfaces radiate less energy per unit area, inflating the calculated radius beyond its true value. These errors can compound if both point in the same direction, pushing the estimate higher or lower than reality, or they can partially cancel if they point in opposite directions, accidentally producing a more accurate result through fortunate error compensation. Without knowing exactly where the errors lie, astronomers must report ranges rather than precise values. Here is your mainstream historical fact for this portion of the journey. The history of astronomy is littered with revised measurements, corrected distances, and retracted claims about record-breaking objects, a pattern that reflects the difficulty of the enterprise rather than any deficiency in the astronomers themselves. Perhaps the most famous example involves the Andromeda Galaxy, whose distance was dramatically revised upward in 1924 when Edwin Hubble identified Cepheids variable stars within it and used their period luminosity relationship to estimate the distance. Before Hubble's work, many astronomers believed Andromeda was a nebula within our own Milky Way galaxy, a nearby cloud of gas rather than a distant island universe. After his measurement, it became clear that Andromeda was a separate galaxy, roughly 2 million light-years away, expanding the known universe by orders of magnitude virtually overnight, and establishing that our galaxy is just one among countless billions. Historians still argue whether Hubble's measurement was the decisive blow that ended the great debate about the scale of the universe, or merely the final confirmation of a shift already underway among astronomers. But the episode illustrates vividly how astronomical understanding can change rapidly when new data and new methods arrive. And here is your quirky tidbit to accompany your journey towards sleep. The largest star ever claimed, briefly and confidently, was an object called UY Scuti, which was reported in 2012 with a radius of approximately 1,708 solar radii, making headlines around the world and entering popular consciousness as the biggest star known to science. Later refinements to the distance estimate and surface temperature reduced UY Scuti's calculated radius significantly, perhaps to around 750 to 1,000 solar radii, dethroning it from record holder status and handing the crown to other candidates. The astronomical community took this revision in stride because measurement refinements are expected and welcomed as science progresses, but the popular press had already moved on to other stories, leaving many people with outdated information about which star truly deserves the title of largest known. If you encounter someone who insists that UY Scuti is the biggest star, you can gently inform them that science has moved forward, which is what science is supposed to do. Several other stars compete with Stephenson 218 for the title of largest known stellar object. Their candidacy is supported by different measurement techniques and different research teams. VY Canis Majoris, a red hypergiant in the constellation Canis Major roughly 4,000 light-years away, has an estimated radius between 1,400 and 1,500 solar radii, depending on the analysis method used. WHG 64, located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way roughly 160,000 light-years distant, may reach 1,500 to 1,700 solar radii, though its extragalactic location makes precise measurement particularly challenging. Westerlund 1-26, residing in the massive cluster Westerlund 1 about 16,000 light-years from Earth, has been estimated at around 1,500 to 2,000 solar radii, with uncertainties large enough that it could potentially rival Stephenson 2-18, depending on which measurements prove most accurate. The scholarly debate about which star is truly the largest involves not just measurement precision, but also definitional questions that have no universally agreed answers. How do you define the edge of a star whose outer atmosphere fades gradually into interstellar space, rather than ending at a sharp boundary? Do you measure the radius to the photosphere, that layer from which most light escapes? Do you use some specific optical depth, some threshold where the stellar material achieves a particular transparency? Do you define the edge by some minimum density, some point where the gas becomes too thin to reasonably call stellar atmosphere? Different choices lead to different numbers, and different research teams make different choices based on different reasoning, complicating direct comparisons between their results. Stephenson 218 currently holds the crown most convincingly, but that crown sits loosely on its head, ready to pass to another whenever better measurements demand a changing of the guard. You meet now the contenders, the other massive stars that compete with Stephenson 218 for the title of largest known stellar object in the universe, each impressive in its own right, each demonstrating that the cosmos produces enormity with something approaching regularity in certain environments under certain conditions. These stars deserve recognition even if they do not currently hold the record, because any of them might claim the crown with revised measurements or improved observations, and because focusing solely on the winner misses the broader story of stellar extremity that the universe tells through all of them. The competition itself reveals as much as the champion, and tonight you have time to appreciate the full roster of cosmic giants. UY Scuti stands as perhaps the most famous of these runners-up, having briefly held the title of largest known star before measurements were refined downward and the crown passed to other heads. Located in the constellation Scutum, coincidentally the same small constellation where Stephenson 2-18 resides, UY Scuti is a pulsating red supergiant approximately 5,000 light-years from Earth, considerably closer than Stephenson 2-18, and therefore somewhat easier to study with available instruments. Its current estimated radius falls somewhere between 750 and 1,000 solar radii depending on which measurements and methods you trust, still enormous by any reasonable standard, still large enough to extend well beyond Jupiter's orbit if placed at the centre of our solar system and consume the inner planets without apparent effort. UY Scuti pulsates irregularly, its brightness varying over periods of roughly 740 days as the star's outer layers expand and contract in complex patterns driven by internal dynamics. This pulsation complicates radius estimates because the star does not maintain a constant size but rather breathes in and out, larger at some times and smaller at others, and different observations catch it at different phases of this breathing cycle. The quoted radius typically represents some average or characteristic value, but the instantaneous radius changes continuously, another reminder that stars are dynamic objects rather than static spheres. Here is your mainstream historical fact for this portion of the journey. V Canis Majoris, another prominent contender for the largest star title, was first catalogued by the French astronomer Joseph-Jérôme Lefrançais de Lalande in 1801, who noted it as a 7th magnitude star, relatively faint to the naked eye and unremarkable among the thousands of dim stars visible through early telescopes. Lalande was conducting a comprehensive survey of the sky, cataloguing positions and brightnesses for future reference, work that required patience and precision but generated little excitement at the time. The true nature of VY Canis Majoris as one of the largest stars in the galaxy was not recognized until 20th century observations revealed its enormous distance and correspondingly tremendous intrinsic luminosity. What appeared as a dim point of light was actually a stellar monster, its brilliance diminished by distance and interstellar absorption to appear as modest as countless ordinary stars. Historians still argue whether Lalande's observations contained any hint of the star's unusual nature or whether it appeared entirely ordinary to his instruments, but the gap between apparent insignificance and true enormity illustrates how profoundly distance deceives our perceptions of cosmic objects. And here is your quirky tidbit to file away for future reference. If V Canis Majoris were placed at the centre of our solar system, its photosphere would likely extend past the orbit of Mars and perhaps reach toward Jupiter, swallowing the terrestrial planets and the asteroid belt with room to spare. The volume of VY Canis Majoris could contain approximately 3 quadrillion Earths, a number so large that writing it out requires 15 digits, and comprehending it requires giving up on comprehension entirely. No human being has ever had a meaningful encounter with a quadrillion of anything, not atoms or grains of sand or seconds of time, making the number effectively meaningless, except as an indicator of scale beyond the reach of intuition, a flag planted at the edge of understanding marking the territory that lies beyond. WOHG 64 presents an intriguing case for different reasons, because it lies outside the Milky Way entirely, situated in the Large Magellanic Cloud, a dwarf galaxy orbiting our own at a distance of roughly 160,000 light-years. This red hypergiant has an estimated radius between 1,500 and 1,700 solar radii, and its extragalactic location makes it both harder to study and scientifically valuable in unique ways. observations of massive stars in other galaxies help astronomers understand whether stellar physics works the same way everywhere, or whether environmental factors like metallicity and galaxy type influence stellar evolution in detectable ways. The Large Magellanic Cloud has lower metallicity than the Milky Way, meaning its stars formed from gas containing fewer heavy elements, and this difference might affect stellar winds and mass loss rates, and ultimately the maximum sizes stars can achieve before losing cohesion. Westerlund 1-26 deserves mention as well, a red supergiant residing in the massive cluster Westerlund 1, located roughly 16,000 light-years from Earth in the constellation Ara. This cluster contains numerous extremely massive stars and represents one of the most concentrated regions of stellar enormity in the entire galaxy, a gathering of giants that rivals or exceeds Stephenson 2 in total mass, and certainly in the diversity of its extreme members. Westerlund 1-26's radius has been estimated at around 1,500 to 2,000 solar radii, with uncertainties large enough that it could potentially rival Stephenson 2-18 depending on which measurements prove most reliable. The pattern emerging from this survey should be clear by now. These enormous stars cluster in particular environments, forming in massive star clusters where initial conditions favour giant creation. They share characteristics: red colours from cool surfaces, high luminosities from enormous total output, variable brightness from unstable layers, and surrounding nebulae of expelled material. They represent a category of stellar extremity that the universe produces regularly, if not abundantly, wherever conditions permit. You focus now on the surface of a hypergiant, attempting to imagine what it would be like to witness such a stellar photosphere up close, to hover somehow near that boundary between star and space, where matter transitions from opaque to transparent and light finally escapes into the universe. This is pure imagination, of course, because no spacecraft could survive such proximity, no material could withstand the conditions, and the very concept of proximity becomes strange when the star itself lacks sharp boundaries. But imagination is the tool we have for exploring places our bodies cannot go, and tonight your imagination serves as your vehicle for visiting the impossible. The surfaces of red hypergiants like Stephenson 2-18 are nothing like the relatively calm photosphere of the Sun. They are roiling, turbulent, dynamic environments where convection cells the size of Earth's orbit rise and fall in slow-motion churning, carrying superheated plasma from the interior to the surface and back again in cycles that take months or years to complete. Imagine standing somehow above this surface, looking down at a landscape that defies all terrestrial comparisons. You would see no solid ground, no liquid ocean, no firm boundary of any kind, just layers of incandescent gas growing gradually denser as you look deeper, eventually becoming opaque below you, the floor of visibility rather than the floor of reality. The convection patterns would create visible texture, regions of slightly different temperature and brightness rising and falling, organizing themselves into granular structures that dwarf entire planets. On the Sun, convection cells called granules span roughly 1,000 kilometers, the size of small countries, and they cycle through their rise and fall patterns in minutes. On a red hypergiant, the equivalent structures might span hundreds of millions of kilometers, larger than the Earth-Sun distance, and their cycles might take months to complete, slow motion tumbling on a scale that makes solar convection look frantic. Here is your mainstream historical fact for this portion of the journey: the understanding that stars have convective layers, regions where energy transport occurs through bulk fluid motion, rather than radiation, developed through the theoretical work of Karl Schwarzschild in the early 20th century. Schwarzschild, the German physicist who also solved Einstein's field equations to describe black holes, developed criteria for determining when a stellar layer would become convectively unstable, when radiative energy transport would prove insufficient and bulk motion would take over. His work established that stars have complex internal structures with different energy transport mechanisms operating at different depths, a picture now confirmed through helioseismology, the study of oscillations in the Sun and other stars. Historians still argue whether Schwarzschild's astrophysical contributions deserve more recognition than his general relativity work or vice versa, but both areas benefited enormously from his mathematical insight. And here is your quirky tidbit for this leg of the journey. Some red hypergiants have been observed to have surface features so large they can be resolved by interferometric techniques, which combine light from multiple telescopes to achieve effective angular resolution far exceeding what any single telescope could manage. Betelgeuse, the famous red supergiant in Orion, has been imaged well enough to show bright and dark patches on its surface, regions of different temperature that change over time as convection cells rise and fall. For the first time in history, we can see surface features on stars other than the Sun, watching alien stellar weather unfold across distances measured in hundreds of light years. The images are crude by photographic standards, mere blobs of slightly different brightness, but they represent a triumph of observational technique and a window into stellar surfaces we could never visit. The instability of hypergiant surfaces manifests in other ways beyond convection. These stars pulse, expanding and contracting in semi-regular rhythms driven by the interaction of opacity, temperature and pressure in their outer layers. The pulsations change the star's brightness and temperature, and even its radius over periods ranging from days to years, making these objects variable stars whose apparent magnitude fluctuates in patterns that astronomers can track and analyze. Some hypergiants show multiple overlapping pulsation periods, different oscillation modes superimposed to create complex brightness curves that require sophisticated analysis to disentangle. The stars also shed mass continuously through powerful stellar winds, streams of particles accelerated off the surface and into space by radiation pressure and other mechanisms. These winds are far more powerful than the solar wind emanating from our Sun, carrying thousands or millions of times more mass per year into the surrounding space. Over the lifetime of a hypergiant, the accumulated mass loss can significantly reduce the star's total mass, stripping away substantial fractions of the original material and leaving the star lighter than it was at birth. This mass loss creates circumstellar nebulae, shells and clouds of expelled material surrounding the star, glowing in infrared light as the hot stellar radiation heats the recently departed gas. The surfaces of these stars are boundaries in transition, thresholds where stellar material becomes thin enough to release its light, where the star's grip loosens enough to let go. They mark the edge of stellar identity, the point past which gas can no longer be claimed by the star and begins its journey into the broader cosmos, and they represent in a sense the star's slow death, the gradual shedding of substance that will eventually leave too little material to maintain fusion, bringing the stellar life to its end. You have glimpsed now the turbulent skin of a dying giant, and you understand why these stars are called unstable, why their brightness varies, why their substance streams away into the darkness. You confront now a paradox that puzzled astronomers for decades before the physics became clear. The larger stars are not the hottest. In fact, they are among the coolest stellar objects in the sky. Their enormous surfaces glowing with temperatures that barely qualify as incandescent by stellar standards. This counterintuitive truth requires some unpacking, some careful thinking about how energy spreads across surfaces and how colour relates to temperature. But the explanation is elegant once you see it, and elegance is restful for a tired mind. Temperature and size tend to move in opposite directions for evolved stars, and the physics behind this relationship follows directly from basic thermodynamics. A star's luminosity, the total energy it radiates per second, depends on both its surface temperature and its surface area. Hotter surfaces radiate more energy per unit area, following the Stephenson-Boltzmann law, which states that radiated power scales with the fourth power of temperature. But larger surfaces have more area from which to radiate, and total luminosity equals the energy per unit area multiplied by the total area. A star can therefore achieve the same luminosity with a hot small surface or a cool large surface, trading temperature against size to produce equivalent power output. When a star expands dramatically during its evolution into a red giant or supergiant, its luminosity typically increases because the core is burning fuel at higher rates during certain phases. But the luminosity increase does not scale as dramatically as the surface area increase. If a star's radius increases by a factor of 1,000, its surface area increases by a factor of 1,000,000, since surface area scales with radius squared. Even if the luminosity increases significantly, say by a factor of 100,000, the energy per unit area drops because there is so much more area to spread that energy across. Less energy per unit area means lower temperature, which means the surface glows red rather than yellow or white or blue. Here is your mainstream historical fact for this portion of the journey. The relationship between stellar colour and temperature was established quantitatively in the late 19th and early 20th centuries through the work of physicists studying blackbody radiation. Max Planck's derivation of the blackbody spectrum in 1900 explained why heated objects glow with colours that shift from red through orange to yellow to white to blue as temperature increases, and this work laid the foundation for quantum mechanics, while also providing astronomers with a tool for measuring stellar temperatures from colour observations alone. Before Planck's work, the connection between colour and temperature was understood qualitatively, but not quantitatively, leaving astronomers unable to assign specific numbers to stellar surfaces. Historians still argue whether Planck's derivation represented a revolutionary break with classical physics or an evolutionary step building naturally on previous work, but the impact on astrophysics was profound regardless of how we classify the conceptual shift. And here is your quirky tidbit to carry forward. The surface temperature of Stephenson 218 at roughly 3,200 Kelvin is actually cooler than a typical candle flame, which burns at around 1,300 to 1,400 degrees Celsius, or about 1,600 Kelvin at its blue base, and up to 1,400 degrees Celsius in its yellow portions. The comparison feels absurd because we think of stars as impossibly hot objects and candles as everyday items barely capable of warming a small room. But the comparison is valid in terms of surface temperature, even if it misses the point entirely in terms of total energy. The candle flame releases perhaps a few dozen watts of power, enough to warm your hands slightly. Stephenson 218 releases approximately 440,000 times the sun's power, which works out to roughly 170 trillion watts, enough energy every second to power human civilization for millions of years if it could somehow be captured and utilized. Same surface temperature, impossibly different total output, all because of scale. The coolness of hypergiant surfaces also explains their red color through the physics of thermal radiation. All objects emit electromagnetic radiation, with a spectrum that depends on their temperature, peaking at shorter wavelengths for hotter objects and longer wavelengths for cooler objects. The Sun, with a surface temperature around 5,500 Kelvin, peaks in the yellow-green portion of the visible spectrum, producing a broad distribution that our eyes perceive as white or slightly yellow. A star with a surface temperature of 3,200 Kelvin peaks in the infrared, with its visible emission concentrated in the red end of the spectrum, producing the characteristic ruddy colour that gives red giants and hypergiants their name. The colour of a star therefore tells you something direct about its surface temperature, serving as a cosmic thermometer, readable from distances of thousands of light years. Blue and white stars are hot, with surface temperatures exceeding 10,000 or even 30,000 Kelvin. Yellow stars like the Sun are intermediate, around 5,000 to 6,000 Kelvin. Orange and red stars are cool by stellar standards, with temperatures dropping below 4,000 Kelvin for the reddest visible stars. The colour-temperature relationship allows astronomers to estimate surface temperatures from photometric observations, measurements of brightness through different coloured filters, without needing detailed spectroscopic analysis for every star. This relationship also creates a curious situation where the largest known stars are not particularly impressive to the naked eye, at least not compared to their intrinsic properties. Stephenson 218, despite being the largest known star, is invisible without telescopes because it lies far away and behind obscuring dust. Even red supergiants visible to the naked eye, like Betelgeuse, appear as ordinary bright stars, their reddish tint the only hint of their extraordinary nature. The universe hides its largest objects behind veils of distance and the deception of angular size, revealing their true nature only to those who look carefully with proper instruments and proper understanding. You consider now the brevity of giant stellar lives, the cosmic irony that the largest and most luminous stars burn through their existence fastest, dying young, while their smaller, dimmer cousins persist for billions of years. This inverse relationship between stellar mass and stellar lifespan represents one of the most fundamental truths of stellar astrophysics, and understanding it helps you appreciate the fleeting nature of objects like Stephenson 2-18, giants that blaze brilliantly for mere moments in cosmic time before collapsing into their final states. The relationship arises directly from the physics of nuclear fusion and gravitational pressure. More massive stars have stronger gravitational fields because they contain more matter, and this stronger gravity creates higher pressures and temperatures in their cores. The higher temperatures drive fusion reactions at faster rates because nuclear reactions are extremely sensitive to temperature, increasing exponentially as the core heats up. A star with 10 times the Sun's mass does not simply fuse hydrogen 10 times faster, it fuses hydrogen roughly 1,000 times faster or more, burning through its fuel supply at a rate that far exceeds the extra fuel available from its greater mass. The result is that massive stars exhaust their hydrogen in millions of years rather than billions. A star like the Sun will remain on the main sequence for approximately 10 billion years, fusing hydrogen steadily, maintaining a stable size and luminosity, providing consistent energy to any planets in its habitable zone. A star with 20 solar masses might remain on the main sequence for only 5 or 10 million years before exhausting its core hydrogen and beginning the expansion into red supergiant territory. A star with 50 solar masses might last only a few million years, barely enough time for planets to form around it, certainly not enough time for complex life to evolve on those planets, even if conditions were otherwise favourable. Here is your mainstream historical fact for this portion of the journey. The relationship between stellar mass and stellar lifespan was first established quantitatively through the work of Arthur Eddington in the 1920s and refined by subsequent researchers through the mid-20th century. Eddington, the British astrophysicist who confirmed Einstein's general relativity through observations of light bending during a solar eclipse, also developed the mass-luminosity relationship for main sequence stars, showing that luminosity increases dramatically with mass. Since more luminous stars burn fuel faster to maintain their greater energy output, and since their fuel supplies do not increase proportionally, the lifespan necessarily decreases. Eddington's work transformed stellar astrophysics from a descriptive to a predictive science, allowing astronomers to estimate stellar ages and evolutionary states from observations of mass and luminosity. Historians still argue whether Eddington's theoretical work or his observational confirmation of relativity represents his greater contribution to physics, but both achievements secured his place among the most influential physicists of the 20th century. And here is your quirky tidbit to accompany this portion of your journey. If the Sun were replaced by a star with 20 times its mass, Earth would be bathed in vastly more intense radiation, surface temperatures would exceed anything compatible with liquid water, and the star would exhaust its hydrogen and expand into a red supergiant before complex life could evolve, even under the most optimistic scenarios for biological evolution. The appearance of multicellular life on Earth required billions of years, time that massive stars simply do not provide. This suggests that life requiring long evolutionary timescales, like the life that produced humans, is more likely to arise around smaller, longer-lived stars than around the brilliant giants that dominate galactic luminosity. The larger stars light up the cosmos but provide poor cradles for the slow development of complexity. Stephenson 218 has already passed through its main sequence phase, already burned through the hydrogen in its core, already expanded into the bloated hypergiant we observe today. Its remaining lifetime is measured in hundreds of thousands of years at most, perhaps less, a cosmic eye blink during which it will continue shedding mass, continue pulsating and fluctuating, continue growing ever more unstable, until finally something gives way, and the star dies in spectacular fashion. The exact timing cannot be predicted with precision, because the final phases of stellar evolution are chaotic and sensitive to conditions we cannot measure remotely, but the outcome is certain. This star will die soon by astronomical standards. When the end comes, Stephenson 218 will likely explode as a supernova, one of the most energetic events in the universe, briefly outshining entire galaxies before fading over weeks and months into an expanding remnant of gas and dust and radiation. The explosion will scatter the star's outer layers across space, enriching the interstellar medium with heavy elements forged during the star's life and during the explosion itself. What remains at the centre will depend on the final mass of the core. If the core is small enough, it will collapse into a neutron star, an incredibly dense object perhaps 20 kilometers across, but containing more mass than the Sun. If the core is too massive even for neutron star support, it will collapse further into a black hole, a gravitational pit from which nothing escapes. The life of a giant is brief but not without consequence. The death of such stars seeds the cosmos with the materials for future generations, for new stars, for planets, for perhaps life itself. You peer now into the future of Stephenson 218, contemplating what will happen when the nuclear fires finally fail and gravity claims its inevitable victory. The death of a hypergiant is not a gentle fading but a catastrophic collapse, a violent end that produces some of the most energetic events in the entire universe. This ending approaches with certainty, even if the precise timing remains unknown, and understanding what will happen helps you appreciate both the grandeur and the transience of cosmic giants. When a massive star like Stephenson 218 exhausts the hydrogen in its core, it does not simply stop burning. Instead, the core contracts and heats until helium can begin fusing into carbon, initiating a new energy source that temporarily halts the collapse. When helium runs out, the core contracts again, heating further until carbon can fuse into heavier elements like neon and oxygen and silicon. Each successive fuel burns faster than the previous one. Each successive contraction raises the core temperature higher, and the star races through a sequence of fusion stages in accelerating tempo. A star that spent millions of years burning hydrogen might spend only a few thousand years burning helium, only a few hundred years burning carbon, only a few years burning oxygen, only days burning silicon. The sequence ends with iron. Iron occupies a unique position in nuclear physics. It has the most tightly bound nucleus of any element, meaning that neither fusing iron into heavier elements nor splitting it into lighter ones releases energy. Both fusion and fission are endothermic for iron, absorbing energy rather than releasing it. When the core of a massive star finally consists primarily of iron, energy production stops, outward pressure fails, and gravity wins the battle that has been waged since the star's birth. Here is your mainstream historical fact for this portion of the journey. The understanding that iron represents an endpoint for stellar fusion was developed through the work of nuclear physicists in the mid-20th century, particularly through the famous B2FH paper published in 1957 by Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle. This landmark paper explained how all the elements heavier than hydrogen and helium are synthesized inside stars through various nuclear processes, establishing the field of stellar nucleosynthesis and earning William Fowler the Nobel Prize in Physics in 1983. The paper showed that elements up to iron are built through successive fusion reactions in stellar cores, while elements heavier than iron require different processes, primarily the rapid neutron capture that occurs during supernova explosions. Historians still argue whether the relative contributions of the four authors have been properly recognised, with Margaret Burbidge in particular sometimes viewed as underappreciated for her role, but the paper itself remains one of the most important in the history of astrophysics. And here is your quirky tidbit for this portion of your journey. The iron core at the heart of a dying massive star, just before it collapses, weighs approximately 1.4 times the mass of the Sun but spans only about the size of Earth, roughly 12,000 kilometers in diameter. This means the density exceeds 1 billion kilograms per cubic meter, so dense that a teaspoon of the material would weigh several tons. This extreme compression results from the loss of electron degeneracy pressure as electrons are squeezed into protons, converting the core into an increasingly neutron-rich state. The core hovers at this extreme density for mere seconds before the final collapse begins, a brief moment of precarious equilibrium before catastrophe. The collapse, when it comes, happens with terrifying speed. The iron core falls inward at a significant fraction of the speed of light, compressing in milliseconds to densities that exceed even the extreme state just described. At these densities, protons and electrons merge to form neutrons, releasing a flood of neutrinos that carry away enormous energy. The collapse halts when the core reaches nuclear density, when neutrons are packed so tightly they literally touch, and the core bounces back slightly, sending a shockwave outward into the infalling material. This shockwave, energized by the neutrinos and the gravitational energy released during collapse, tears through the star's outer layers, heating and accelerating them to velocities of thousands of kilometers per second. The result is a supernova explosion, one of the most luminous events in the universe, briefly outshining billions of ordinary stars, visible across millions of light years, a beacon announcing the death of a giant to anyone watching from any distance. For Stephenson 2-18, the supernova will occur somewhere between now and perhaps 100,000 years from now, an estimate so imprecise it barely qualifies as a prediction, but represents the best astronomers can do given the complex, chaotic nature of the final stellar phases. When it happens, the event will be visible from Earth, despite the 20,000 light-year distance and intervening dust, appearing as a bright new star in the constellation Scutum, persisting for weeks or months before fading. The last supernova visible to the naked eye from Earth occurred in 1604, over 4 centuries ago, so a new one would be a significant astronomical event, though Stephenson 2-18's distance and the intervening dust might make it less spectacular than closer explosions would be. After the explosion, a remnant will remain. Likely a neutron star, possibly a black hole, depending on the final mass of the collapsing core. You trace now the aftermath of stellar death, following the scattered remains of exploded giants as they spread across space and eventually contribute to the formation of new stars, new planets, and perhaps new life. The supernova explosion that ends the life of a star like Stephenson 218 is not merely a destruction, but also a creation, a cosmic recycling event that transforms the heavy elements forged inside the dying star into raw materials for future generations. This cycle of stellar birth, death, and rebirth represents one of the most profound processes in the universe, connecting the largest structures to the smallest atoms in an unbroken chain of cosmic chemistry. When a massive star explodes as a supernova, its outer layers are expelled at velocities of thousands of kilometers per second, carrying with them all the elements synthesized during the star's life and during the explosion itself. Carbon and oxygen from helium burning, neon and magnesium from carbon burning, silicon and sulfur from oxygen burning, iron and nickel from the final silicon burning, and dozens of heavier elements created through rapid neutron capture during the explosion itself. All of this material streams outward into interstellar space, mixing with the surrounding gas, enriching the cosmic medium with the building blocks of future complexity. This enriched material does not dissipate uniformly, but rather forms an expanding shell called a supernova remnant, a bubble of hot gas bounded by a shock wave ploughing into the surrounding interstellar medium. The remnant glows across multiple wavelengths, radiating X-rays from its hottest regions, optical light from cooling gases, and radio waves from electrons spiraling in magnetic fields. Over thousands of years, the remnant expands and cools, eventually merging with the general interstellar medium and losing its distinct identity, but the enrichment it provided remains, incorporated into the gas clouds that drift through the galaxy. Here is your mainstream historical fact for this portion of the journey. The first supernova remnant to be clearly identified as such was the Crab Nebula, the expanding debris from a supernova observed by Chinese astronomers in 1054 CE. Chinese records describe a guest star appearing in the constellation we call Taurus, bright enough to be visible in daylight for several weeks, then gradually fading over 2 years. The expanding nebula we observe today corresponds precisely to the position and age expected from that historical record, providing a remarkable connection between ancient observation and modern astrophysics. The Crab Nebula has been studied extensively and remains one of the best understood supernova remnants, harbouring a rapidly rotating neutron star called a pulsar at its centre that powers the nebula's continued glow. Historians still argue whether European and Islamic astronomers also recorded the 1054 supernova and their records were simply lost, or whether cultural factors led non-Chinese observers to dismiss or ignore the celestial event. And here is your quirky tidbit to carry into your dreams. The calcium in your bones was likely forged inside a massive star billions of years ago, ejected in a supernova explosion, scattered across interstellar space, eventually incorporated into a molecular cloud, then into the forming solar system, then into the planet Earth, then into the food you ate, and finally into your skeleton. The same is true for the iron in your blood, the carbon in your DNA, the oxygen you breathe. You are quite literally made of star stuff, assembled from atoms forged in cosmic furnaces and scattered by cosmic explosions. This is not a metaphor or a poetic fancy, but a straightforward physical truth, traceable through nuclear physics and cosmic chemistry. Carl Sagan popularized this perspective, though he was not the first to articulate it, and it remains one of the most profound insights astronomy offers. We are not merely observers of the universe, but products of it, connected to the largest structures through our smallest components. The enriched material from supernovae eventually participates in new cycles of star formation. Giant molecular clouds slowly accumulate heavier elements through successive generations of stellar death, their composition evolving over cosmic time from nearly pure hydrogen and helium to gas mixtures containing measurable amounts of carbon, oxygen, silicon, iron, and other elements. When these enriched clouds collapse to form new stars, the resulting stellar systems contain more heavy elements than their predecessors, enabling the formation of rocky planets, complex chemistry, and potentially life. The Sun formed from a molecular cloud already enriched by multiple generations of stellar nucleosynthesis, which is why the solar system contains abundant heavy elements, despite hydrogen and helium still dominating the overall composition. The Earth exists because previous generations of stars lived and died and scattered their remains, providing the raw materials from which our planet condensed. The life that arose on Earth exists because those raw materials included carbon and oxygen and nitrogen and phosphorus and all the other elements biochemistry requires. Stephenson 218, when it eventually explodes, will contribute to this ongoing enrichment, scattering heavy elements that will someday participate in forming new stars and perhaps new worlds orbiting those stars. The atoms currently comprising the star's outer layers will travel through the galaxy for millions or billions of years before finding new homes, new roles, new purposes in the cosmic story. Nothing is wasted in the universe, only transformed, and the death of a giant ensures the birth of countless smaller things. You allow yourself now to wonder about the possibility of life around such enormous stars, to ask whether planets might orbit these giants, and whether those planets might harbour anything we would recognise as living. This speculation ventures into territory where hard science gives way to educated guessing, where we must acknowledge vast uncertainties while still finding interesting questions worth exploring. The nature of habitability around hypergiants tells us something about the conditions life requires and the circumstances the universe most readily provides. The short answer is that life as we know it almost certainly cannot exist around stars like Stephenson 2-18, and the reasons compound upon each other in ways that make the prohibition nearly absolute. The star's lifespan is too short for biological evolution to proceed, its radiation environment too variable and extreme, its gravitational influence too chaotic for stable planetary orbits in temperate zones. Each factor alone would present serious challenges. Together they render the prospect essentially impossible by any reasonable assessment. Consider first the timescale problem. Life on Earth required billions of years to progress from the first self-replicating molecules to complex multicellular organisms, and the emergence of intelligence required nearly the full 4 billion years of biological history. A star like Stephenson 218 exists for mere millions of years in total, with its hypergiant phase lasting perhaps hundreds of thousands of years at most. Even if planets existed around the star's progenitor during its main sequence phase, that phase was too brief for life to develop beyond perhaps the most primitive microbial stages, assuming life could get started at all under the intense radiation environment. Here is your mainstream historical fact for this portion of the journey. The concept of a habitable zone around stars, the range of orbital distances where liquid water might exist on a planet's surface, was first articulated in recognizable form by astrophysicist Su Huang in 1959, building on earlier ideas about conditions necessary for life. Huang recognized that stellar luminosity and surface temperature determine the location and width of habitable zones, and he noted that stars of different masses would have habitable zones at different distances with different characteristics. The concept has been refined and complicated since then, with modern researchers considering factors like atmospheric composition, planetary rotation, and stellar activity. But Huang's basic framework remains foundational for astrobiology. Historians still argue whether Huang deserves primary credit for the habitable zone concept, or whether he synthesized ideas already implicit in earlier work, but his 1959 paper clearly established the framework that guides modern searches for potentially habitable exoplanets. And here is your quirky tidbit for this stage of the journey. The habitable zone around a star like Stephenson 218 would lie at an enormous distance from the star, perhaps several hundred astronomical units, roughly the distance from the Sun to the outer reaches of the Kuiper belt. At such distances, orbital periods would span centuries or millennia, and the gravitational binding to the star would be weak enough that passing stars or internal perturbations could easily disrupt planetary orbits. A planet attempting to maintain stable conditions for life would face chaotic gravitational influences, variable stellar luminosity as the hypergiant pulses, and periodic mass loss events that would dramatically alter the surrounding environment. The habitable zone would be a dangerous neighbourhood, changing in location and character as the star evolved, and no planet could plausibly track those changes while maintaining surface conditions compatible with life. The radiation environment presents additional problems beyond simple luminosity considerations. Red hypergiants emit powerful stellar winds that carry radiation and energetic particles far into surrounding space, bathing any nearby planets in conditions that would strip atmospheres and sterilize surfaces. The X-ray and ultraviolet output, while less intense than from hotter stars, still poses challenges for biological molecules, and the variable nature of hypergiant luminosity means that any planet in a marginal habitable zone would experience dramatic temperature swings as the star pulses brighter and dimmer over periods of months to years. Perhaps most fundamentally, we do not observe planets around red supergiants or hypergiants, and we have theoretical reasons to doubt they could survive the star's evolution, even if they had formed earlier. When a star expands from main sequence dimensions to hypergiant dimensions, any planets in close orbits are simply engulfed, absorbed into the stellar envelope and destroyed. Planets at greater distances might survive the expansion, but they would then find themselves in very different orbital environments, with the star's mass loss changing the gravitational dynamics and the luminosity changes altering surface conditions dramatically. The universe apparently did not design red hypergiants as homes for life, but rather as element factories, as engines for converting light elements into heavy ones and scattering those heavy elements across space for future use. Their role in the cosmic story is not to nurture but to create, to forge the materials that will eventually find their way into smaller, more stable stellar systems, where the patient work of biological evolution can proceed. Stephenson 218 will never host a living world, but its death will contribute to countless future worlds where life might eventually emerge. This is perhaps the most profound perspective. The giant dies so that others might live, sacrificing its short existence to seed the cosmos with the possibility of complexity. You look now toward the future of astronomical discovery, toward the stars we have not yet found hiding in unexplored regions of the galaxy, obscured by dust or simply overlooked by surveys not yet comprehensive enough to catalogue every giant lurking in the cosmic darkness. The current champion, Stephenson 218, holds its title provisionally, subject to revision whenever better measurements arrive or larger stars are discovered in regions we've not yet adequately searched. The universe almost certainly contains stars we have not yet met, and some of them may exceed even the current record holder in size. The limitations of current observations leave substantial room for future discoveries. Our view of the galaxy is heavily obscured by interstellar dust, particularly toward the galactic centre and along the plane of the Milky Way where most massive stars are born and live. infrared surveys have pierced some of this obscuration, revealing stars like Stephenson 2-18 that would be invisible in optical wavelengths. But infrared observations have their own limitations and cannot detect every hidden giant. The regions behind the galactic centre, on the far side of the Milky Way from our solar system's position, remain particularly poorly catalogued, and massive star clusters in those regions could contain red hypergiants, rivaling or exceeding known examples. The upcoming generation of telescopes promises to expand our view dramatically. Space-based infrared observatories like the James Webb Space Telescope, already operational and producing remarkable results, can peer through dusty regions with unprecedented sensitivity, identifying embedded massive stars that previous instruments could not detect. Ground-based extremely large telescopes under construction, with primary mirrors exceeding 20 or 30 meters in diameter, will achieve angular resolution capable of resolving surface features on distant giants and measuring their properties with precision currently impossible. Here is your mainstream historical fact for this portion of the journey. The discovery of increasingly large stars has tracked improvements in observational technology throughout astronomical history. When visual observations from small telescopes dominated the field, the largest known stars were nearby red giants visible to modest instruments. As photographic surveys expanded coverage and infrared detectors enabled observations through dust, larger and more distant giants emerged from obscurity. The infrared astronomical satellite, launched in 1983, conducted the first all-sky survey at infrared wavelengths and identified numerous luminous, cool stars that had been missed by optical surveys. Subsequent infrared missions have continued this pattern, revealing red supergiants and hypergiants hiding behind dusty veils. Historians still argue whether observational advances or theoretical predictions have driven progress in understanding massive stellar evolution more powerfully, but the interplay between improved instruments and new discoveries clearly follows a pattern of mutual reinforcement. And here is your quirky tidbit for this portion of your journey. Theoretical models suggest that there may be an upper limit to how large a star can become, a maximum radius beyond which stellar structure cannot remain coherent, and the star simply falls apart through runaway mass loss. This theoretical maximum radius has been estimated at roughly 2,000 to 3,000 solar radii, depending on assumptions about stellar winds and internal structure, which means Stephenson 2-18 approaches but does not necessarily reach the absolute limit. If stars larger than 3,000 solar radii cannot exist even in principle, then the largest star possible lies not far beyond what we have already found, and the record might be approached asymptotically rather than dramatically exceeded. On the other hand, the theoretical models carry significant uncertainties, and nature has a history of surprising theorists with phenomena they did not anticipate. Other galaxies almost certainly contain red hypergiants comparable to those in the Milky Way, and some may contain examples larger than anything in our own galaxy. The Large and Small Magellanic Clouds, satellite galaxies visible from the southern hemisphere, have been surveyed extensively and contain massive stars including WOHG 64 mentioned earlier. More distant galaxies are harder to study at the resolution needed to identify individual stars, but future facilities may enable surveys of massive stellar populations in galaxies throughout the local group and beyond. The discovery of even larger stars would not necessarily change our fundamental understanding of stellar physics, but would refine the boundaries of what is possible, mapping the extremes of cosmic structure with greater precision. Each new record holder demonstrates that the universe produces objects at the edge of theoretical possibility, pushing against physical limits, exploring the full parameter space of what can exist. Finding a star larger than Stephenson 2-18 would be exciting news, headline material for astronomy enthusiasts and science journalists, but it would also be unsurprising in a sense, confirming that our current catalogue remains incomplete and that exploration always reveals new wonders. The search continues, as searches in science always do, driven by curiosity and enabled by improving technology. Somewhere out there, perhaps in a dusty cluster behind the galactic centre, perhaps in an obscured region of a satellite galaxy, perhaps in a location we cannot currently observe, the true largest star in the universe awaits discovery. Stephenson, 218 holds the title for now, but titles in science are always temporary, placeholders marking our current knowledge rather than permanent monuments to eternal truths. You arrive now at the end of your journey through the realm of stellar giants, having travelled from familiar solar dimensions through red giant expansions and supergiant enormities to the current champion of cosmic scale, Stephenson 218, a star so vast it defies easy comprehension. The voyage has carried you through physics and history, through measurement techniques and philosophical questions, through the life cycles of stars and the cycles of cosmic enrichment that connect stellar death to the possibility of life. Now, as your eyelids grow heavy and your thoughts begin to soften around the edges, it is time to let the cosmic immensities fade into comfortable darkness, to let the numbers and the names drift away like clouds dissipating in a warming sky. Think for a moment about what you have encountered tonight. You have met a star whose radius exceeds 2,000 times that of the Sun, a sphere so large that if placed where the Sun currently sits, its surface would extend past Saturn and approach Uranus, engulfing everything from Mercury to the asteroid belt to Jupiter and beyond. You have learned that this star, despite its enormous volume, contains only modest mass by stellar standards. A cosmic soap bubble inflated to extraordinary dimensions. You've discovered that the largest stars are paradoxically among the coolest, their immense surfaces spreading their energy so thin that they glow with temperatures below a candle flame. You've traced the birth of giants from collapsing molecular clouds and anticipated their deaths in supernova explosions that scatter heavy elements across space. Here is your final mainstream historical fact for this sleepy journey. The human understanding of stellar scale has expanded dramatically over just a few centuries, from ancient beliefs that stars were holes in a celestial sphere or lamps hung for human benefit, to the modern comprehension of nuclear furnaces spanning dimensions that would take light hours to cross. This expansion of understanding represents one of humanity's greatest intellectual achievements, a triumph of curiosity and persistence and clever reasoning applied to pinpricks of light impossibly far away. The astronomers who built this understanding worked across generations, each adding pieces to a puzzle that no single lifetime could complete, and their collective effort produced a vision of the cosmos that previous generations could not have imagined. And here is your final quirky tidbit. If you could somehow travel to Stephenson 218 and hover above its turbulent surface, watching convection cells the size of planetary orbits rise and fall in slow motion, you would witness a sight no human eye was ever designed to see, a landscape so far beyond earthly experience that words could only gesture toward its reality. The star does not know you're thinking about it tonight, does not care about human categories or record books or sleepy science videos. It simply exists, doing what stars do, fusing and pulsing and shedding mass into the void, following the physics that governs all matter and energy throughout the universe. And yet, here you are, a small collection of atoms on a small planet orbiting a modest star, somehow able to comprehend the existence of this giant, to hold its dimensions in your mind even as those dimensions exceed your direct experience. That is remarkable. You are remarkable for being able to do this. The universe is vast beyond measure, and the largest star within it serves as a reminder of that vastness, a landmark at the edge of the possible, a monument to scale that challenges human intuition and rewards patient contemplation. And now, as the cosmic giants recede into comfortable distance, let yourself sink deeper into the warmth surrounding you. The numbers do not matter anymore, not really. What matters is the softness of your pillow, the gentle rhythm of your breathing, the way your body feels heavier and more relaxed with each passing moment. The stars will continue their ancient dance whether you watch them or not. Stephenson 218 will pulse and shed, and eventually die in spectacular fashion. But that is a problem for future astronomers to observe, not for you to worry about tonight. Your only task now is to let go, to release the day's concerns along with the cosmic measurements, to allow your thoughts to become as light and diffuse as the outer atmosphere of a red hypergiant, spreading thin, growing calm, fading into peaceful darkness. Imagine yourself floating now, not in the violent space near a massive star, but in the gentle void between galaxies, where nothing demands your attention, where no light is too bright, where silence stretches in every direction like the softest blanket ever woven. The universe holds you, as it holds all things, with the patient gravity of existence itself. Your eyes are closed or closing. Your breathing has slowed to match the rhythm of something deeper than thought. The largest star in the universe is very far away, and you're exactly where you need to be, warm and safe and drifting toward dreams. Sleep now. Let the giants fade. Let the light years collapse into the comfortable distance of rest. Tomorrow the universe will still be there, vast and strange and wonderful, waiting for you to wonder at it again. But for now, just sleep. Sweet dreams.